Take a look at some of these. These are just some, these are difficult descriptions of what happens in a lab, and you're supposed to write out, now notice that it's asking for the net ionic equation. You can tell that by seeing when they show you like a plus and a minus like this. It doesn't have to be balanced, you're just writing out what is interacting with what and leaving out spectator ions. That's what it's asking you to do. Seems like it would be pretty easy, but they want you to focus on how, it says omit formulas for any ions or molecules that are unchanged by the reaction. You need not balance the equation. So a strip of zinc is placed in a solution of nickel 2 nitrate. That's the first one. So what I'm going to do is I'm going to go through the first 4 here and see if I can explain what's going on. And then we'll go through the next 4 on the next podcast, or our next screencast, if I take too long. Otherwise, we'll just jump right into them. So here's what's going to happen. Now I'm going to jump in front here. A strip of zinc is placed in a solution of nickel 2 nitrate. So what happens with that is, here we have, for letter A, I have my zinc. It says a strip of zinc. That means solid. That means I don't have to write any of that. Plus, and then nickel 2 nitrate. Now, so it's your job to know how to put this together. Nickel 2 nitrate looks like this. It's a, there we go. Plus 2 here and minus 1 for nitrate. You may want to look at the polyatomic ions again. In this situation, this is a straight signal displacement reaction. What does that mean? That means that A is can be positive, plus 2, nickel's positive, so A and B switch places, and C here, the negative part of the compound is then like, so if it's switched, it looks like this, ZnNO3 minus, well, minus 1 doesn't show up. Don't do that. Don't, crap. Give me a second here because this thing sucks. Okay. So that's NO3 with a minus 2 like that. Now here's what you need to recognize. You need to recognize that if we write out charges, what you get is this. See, I screwed it up there. 2NO3 with a minus 1. On this side, it's nickel and zinc with a plus 2, plus 2NO3 with a minus 1. Now, we don't have to balance anything, right? And we should get rid of spectator ions. What are spectator ions? Spectator ions are those things that do not change from one side to the other. See here, nickel goes from a plus 2 to 0. That's a charge of 0. Over here, zinc goes from 0 to a charge of plus 2. So that does change. Those two do change because they change in charge. Or you can change in state where it goes from gas to a liquid or something like that. But here, or you can have something goes from dissolved in water to a weak acid, and that would also be considered a change. And I'll get more into that then, because I'm sure there's one of those examples on here. So that means we can get rid of this, we can get rid of this, and what it looks like when I'm finished is just zinc, and you don't even have to put in the, it's just zinc like this, plus nickel 2 with a plus 2, and then this goes to nickel with a zinc as a plus 2. That's it. That right there is the answer, okay? That's what you can reduce it down to get it correct. That took a little bit longer than I thought it was going to. So let's take this and move it up. Like that, and move it up to here. Like this, and then that's it. And now I'm going to get rid of the rest of this stuff here. And let's take a look at the next one. So the next one looks like solid aluminum hydroxide is added to a concentrated solution of potassium hydroxide. Oh, 2 hydroxides. Okay, let's write this out and see what we got. solid aluminum hydroxide. Aluminum is a +3, which means with hydroxide is a -1. Potassium hydroxide is KOH because a +1 and a -1. And then on this side, now here's where stuff gets a little like poopy. Here's where stuff gets a little messed up. So here my potassium doesn't change at all because there's always going to be ions in the water, but this attaches itself over here. This is something that is very strange. That is not something that I typically teach, but what you'll notice is that what I've developed here is a polyatomic ion. The polyatomic ion is aluminum hydroxide where there's an extra hydroxide. Okay, now that means that I got potassium with a +1 here floating around. The problem with potassium as a +1 is that if it's here and it's here as a +1, it has now become a spectator ion. Now we don't have to balance anything, but I am going to have to show the hydroxide plus OH minus like this goes to aluminum the 4 with a -1 like that. Okay, that's a strange situation. I wouldn't expect you to come up with that one on your own. They do. I'm not sure why we don't go over hydroxides turning into polyatomic ions. That's not something that we typically do. But that's the answer to that one. So let me put that one up in the corner, or put that one up under letter B. And I'll get back to you. Okay. All right, moving on. Okay. So how about ethyne? Ethyne is also known as acetylene. Acetylene, for letter C, is C2H2. If you don't know that, then you should Google it to see what it is. Burns in air means +O2. On the other side, when we have carbon and hydrogen, a hydrocarbon, we can only have two choices. The choices are carbon dioxide and water. So now we just go back through and check to see. We don't have to balance anything, so it doesn't matter. We check to see if there's anything, is there any kind of, doesn't look like there's any spectator ions, because these are all non-metals, which means we really don't have ions at all. We have non-metal interactions are more about non-polar covalent bonds and no ions. Okay, so I'm going to slide right into D here. So D says solid calcium with a +2, carbonate is CO3 with a -2, plus a solution of ethanoic or acetic acid. That is my HC2H3O2. Acetate is a polyatomic ion that we learned, so you should be able to do that. Now we're simply going to, now this ends up being A, B, C, and D. So what I'm going to do then is do my double displacement where A goes with D. So that's going to be CA, okay, C2H3O2 like this, and then a 2 here like that, and then my H goes with H2CO3. This is a weak acid. Okay, that's a weak acid, and this is a weak acid. So we do not separate them, but we still do, we do not separate them, so there really is nothing we can do here. Now, there are times when you will have carbonate breaking up into carbonic acid and water, or not carbonic acid, but carbon dioxide and water. So this would be one of those cases. Let me just scroll down here so we can see this, because I'm going to start off with a -2 here like this, and a lot of times if there's an H involved, maybe I should do this, plus H plus like this, and we can end up with H2O plus CO2 for carbonic acid or carbonate in the presence of an acid. Okay, and you'll see this. This is what all the bubbling is about. You probably have seen this already in the lab, either from Honors Chem when we did that big 13 reaction lab, or from somewhere else. So if I combine these two and I get rid of this and do this, then what I have for letter D is, and this has got to all stay because there are no let me just write this out. There are no spectator ions, so that would be CaC2H3O2 like this, and that's a 2 there, plus CO2 plus H2O, and that would be, that's it. All right, that's the first 4.